Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from the Department of Physics, Central University of Haryana. Today we are going to discuss about the module Quantum Dynamics, the Heisenberg picture under the paper Quantum Mechanics 1. So students, let us see what are we going to learn in this module. Firstly, we'll learn about the Heisenberg picture. Then, we'll derive the expressions for the Heisenberg's equations of motion. After that, we'll learn how the problem of linear harmonic oscillator is studied through the Heisenberg's equations of motion. Then, we'll learn the similarity between the equations of motions in quantum dynamics and those in classical mechanics. Now, the main objective of non-relativistic quantum dynamics is to determine the variables or parameters that specify the state of a physical system, and secondly, to describe the time evolution of the system. While there are many possible representations of wave functions and observables connected by unitary transformations, it is useful to identify certain classes of representations called pictures which differ in the way the time evolution of the system is developed. In the preceding module, we studied how the state of an arbitrary time is determined from a given initial state through the time evolution operator, and learnt the basic properties of this operator. In the Schrödinger picture, where the dynamical variables are time independent, we set up the equations of motion involving the evolution in time of the expectation values of the corresponding Hermitian operators. In this module, we study how in the Heisenberg picture, time-independent state vector is related through the unitary transformation to the state in the Schrödinger picture, and then derive the Heisenberg equations of motion for the time-dependent Heisenberg operators. We shall show that the equations of motion for the expectation values of the observables in the Heisenberg picture and the Schrödinger picture are the same. Finally, we point out the correspondence and the similarity of the equations of motion for the expectation values of the operators in quantum mechanics with those of the dynamical variables in classical mechanics. Heisenberg equations of motion. In the Heisenberg picture, the time-independent state vector is related through unitary transformation to the state vector in the Schrödinger picture. That is, if we have a state vector, ket vector psi subscript h, which is defined in the Heisenberg formulation, then the state vector ket vector psi subscript h is equal to unitary operator u dagger t t naught acting on the ket vector psi t in the Schrödinger formalism, where the ket vector psi st, that is the ket vector in the Schrödinger formalism, is equal to unitary operator t t naught acting on ket vector psi s as a function of t naught, where psi s t naught is the state vector in the Schrödinger formalism. Therefore, we can define, or rather we can rewrite the ket vector psi h, that is the state vector in the Heisenberg formalism, as being equal to unitary operator dagger u t t naught, unitary operator u t t naught acting on ket vector psi s t naught. And this gives us the result ket vector psi h in the Heisenberg formalism is equal to ket vector psi s t naught in the Schrodinger formalism, where the unitary operator u dagger, unitary operator u is equal to unit operator. Thus, we can see that in the Heisenberg picture, the state vector psi s t naught, the ket vector psi s t naught of the Schrodinger formalism, which is a constant in time, is equal to the ket vector psi h, or the state vector in the Heisenberg formalism. Thus, the Heisenberg equations of motion can be derived from this formalism that we have just discussed. And to find the relation between the operator A subscript h and the operator A subscript s, the earlier operator being defined in the Heisenberg picture and the latter operator being defined in the Schrodinger picture, then we can suppose that the operator A subscript h acting on the ket vector psi subscript h is equal to ket vector phi subscript h, and similarly the operator A subscript s acting on ket vector psi subscript s is equal to ket vector phi subscript s, where the subscript h denotes the Heisenberg picture and the subscript s denotes the Schrodinger picture. Heisenberg equations of motion. Now, the way we have defined operator A subscript h in the Heisenberg picture and the operator A subscript s in the Schrodinger picture, that is, operator A subscript h acting on ket vector psi h is equal to ket vector phi h, and operator A subscript s acting on ket vector psi s is equal to ket vector phi s, it is easy to show that the operator A subscript h t is equal to operator u dagger t t naught, operator A subscript s, operator u t t naught, where operator u dagger t t naught and operator u t t naught are the unitary operators and are the complex conjugate of each other. This equation shows that the operator A subscript h t in the Heisenberg formalism generally depends on time, even if the operator A subscript s does not. That means that even if an operator does not depend on time in the Schrodinger formalism, yet the operator as defined in the Heisenberg formalism can still depend upon time. Thus, we can define the time derivative of the operator A subscript h t in the Heisenberg picture as the derivative of operator A subscript h t with respect to time is equal to the partial derivative with respect to time of the unitary operator u dagger, operator A s subscript s, unitary operator u t t naught plus unitary operator u dagger, operator A subscript s, partial derivative with respect to time of unitary operator u. We know that the partial derivative with respect to time of the unitary operator u is equal to minus I by h cross whole times operator h, operator u, where operator h is the Hamiltonian operator and the operator u is the unitary operator. Similarly, we can also define the partial derivative with respect to time of the unitary operator u dagger, which is equal to iota by h cross whole times unitary operator u dagger times the Hamiltonian operator h. It thus follows that the derivative of the operator AHT with respect to time turns out to be equal to I by or iota by h cross times within brackets unitary operator u dagger, Hamiltonian operator h, operator A subscript s unitary operator u t t naught minus unitary operator u dagger operator a subscript s Hamiltonian operator h unitary operator u, and this turns out to be equal to iota by h cross times within brackets unitary operator dagger u dagger times the Hamiltonian operator h times the unitary operator u times the unitary operator u dagger plus operator a subscript s unitary operator u minus unitary operator u dagger times operator a subscript s times operator u times operator u dagger times Hamiltonian operator h times unitary operator u. So in this equation, if we carefully notice, we will see that what we have done is that on the right hand side of the equation, within the brackets, both in the first term as well as the second term, we have introduced a unit operator matrix which is defined by the product of the unitary operator u times the unitary operator u dagger. So in this way, by introducing this term, we can actually get the commutation relation between the Hamiltonian operator and the operator A in the Heisenberg picture. So now coming back to the equation, if we look at the final result, we have the final result as iota by h cross times within brackets Hamiltonian operator subscript h, A operator subscript h minus A operator subscript h, Hamiltonian operator subscript h, where we have used the definition for the Hamiltonian operator in the Heisenberg formalism to define the Hamiltonian operator h subscript h, and we have used the definition of the operator A in the Heisenberg picture as a relation with the operator A in the Schrödinger picture. So using those two results that we have discussed earlier, we have obtained this final equation. And from this equation, we can see that the second term within brackets on the right hand side is the commutation relation between the Hamiltonian operator AH and the operator AH. So we can write the final result as the time derivative of the operator A subscript HT is equal to 1 upon iota times h cross commutation relation of operator A subscript H and operator H subscript H, where if you see that we have taken the iota in the denominator so that the sign gets reversed, and hence we get this final commutation relation between the operator A subscript H and the Hamiltonian operator H subscript H in the Heisenberg picture. Thus, if operator A depends explicitly on time, then we can write the time derivative of the operator A subscript HT as partial derivative with respect to time of operator A subscript H plus 1 upon iota times h cross commutation relation of operator A subscript H with the Hamiltonian operator H subscript H in the Heisenberg picture. These equations are called equations of motion for the operator A subscript H t. Equations of motion for the position operator x and the corresponding momentum operator px. Now, the equations of motion for the canonical position and momentum operators can be found in the following manner. Since the operators are time independent in the Schrödinger picture, that is, the position operator x and the momentum operator px are independent of time, or in other words, the partial derivative of the position operator with respect to time is equal to 0. Similarly, the partial derivative of the momentum operator px with respect to time is also 0 in the Schrödinger picture. Therefore, we have the derivative of the position operator in the Heisenberg picture with respect to time is given as 1 upon iota times h cross whole times the commutator of the position operator in the Heisenberg picture and the Hamiltonian in the Heisenberg picture. Similarly, the derivative of the momentum operator px in the Heisenberg picture with respect to time, that is d by dt of the momentum operator px in the Heisenberg picture, is equal to 1 upon iota times h cross whole times the commutator between the momentum operator px in the Heisenberg picture and the Hamiltonian operator in the Heisenberg picture. From here, we can extend these results to the case when the Hamiltonian operator is a function of the position operator x and the momentum operator px. Then the commutation relations are given as the commutator of the position operator x with the Hamiltonian operator h is equal to I h cross, that is iota times h cross, partial derivative with respect to the momentum operator px of the Hamiltonian operator h, and similarly the commutator of the momentum operator px with the Hamiltonian operator h is given as being equal to minus iota times h cross the partial derivative of the Hamiltonian operator with respect to the position operator. Here it is important to note that we drop the suffix h to represent the Heisenberg picture because now the discussion is in the Heisenberg picture only. Linear harmonic oscillator in Heisenberg picture. Now let us look at how we can define the linear harmonic oscillator in the Heisenberg picture. Here, the operators are time dependent in comparison to the operators in the Schrödinger picture where they are time independent, and therefore in the Heisenberg picture using time dependent operators, the Hamiltonian can be defined as a function of time, or the Hamiltonian operator ht in the Heisenberg picture is defined as operator ht is equal to square of the momentum operator t upon twice m, where m is the mass, plus half times k square of the operator x t, where operator pt is the momentum operator in the Heisenberg picture and operator xt is the position operator in the Heisenberg picture, and k is the elastic constant of the simple harmonic oscillator. Thus, the Hamiltonian operator ht in the Heisenberg picture can then be further simplified as 1 upon twice m times within brackets square of the momentum operator pt plus square of the mass times square of the angular frequency times square of the position operator xt. Thus, equations of motion for the momentum operator p and the position operator x are derivative with respect to time of the position operator x is equal to partial derivative with respect to the momentum operator p of the Hamiltonian operator h, and this is equal to momentum operator p upon m. Similarly, the time derivative of the momentum operator p is equal to minus partial derivative with respect to the position operator of the Hamiltonian operator h, and this is equal to minus mass times square of the angular frequency times the position operator x. Differentiating this equation with respect to time and substituting for the derivative of the momentum operator with respect to time from the equation for the momentum operator in the above equation, which defines the time derivative of the position operator, we get the double derivative with respect to time of the position operator plus the square of the angular momentum times position operator x is equal to 0. And this is the same equation that we have in classical mechanics for defining the equation of motion of the linear harmonic oscillator. This second order differential equation can then be solved and can give us the following solutions. Solution of harmonic oscillator. Now, if we look at the equation of motion of the harmonic oscillator in the Heisenberg picture, which is given as the double derivative with respect to time of the position operator x plus square of the angular frequency times position operator x is equal to 0, then the solution to the second order differential equation is of the form position operator x as a function of time is equal to operator c subscript 1 times exponential within brackets minus iota omega t plus operator c subscript 2 times exponential within brackets iota omega t, where omega is the angular frequency, and this can be written as operator a subscript 1 cos of omega t plus operator a subscript 2 sine of omega t, where operator a subscript 1 is equal to operator x at time t equal to 0 is equal to operator x naught, and operator a subscript 2 is equal to 1 upon omega times differentiation of operator x with respect to time, and this is equivalent to operator p at time t equal to 0 upon m omega, and this is equal to operator p naught upon m omega. Here we have used the result for the derivative of the position operator x with respect to time in terms of the momentum operator p. Thus, we have operator x as a function of time is equal to operator x naught cos omega t plus operator p naught upon m omega times sine omega t, where we have used the results for operator a subscript 1 and operator a subscript 2 and substituted these in the equation for the solution of the position operator as a function of time. Similarly, we can also write the equation for the momentum operator as a function of time, and this is equal to mass times the derivative of the position operator x with respect to time, and this turns out to be equal to operator p naught cos omega t minus mass times angular frequency times operator x naught times sine omega t. Substituting these in the Hamiltonian, we get the Hamiltonian operator h is equal to 1 upon twice mass times within brackets operator p naught square plus mass square times angular frequency square times operator x naught square. And we see that the Hamiltonian operator as defined in this equation is independent of time. Here the momentum operator p naught and the position operator x naught are both time independent operators. Solutions of harmonic oscillator. They are identical, or we can say that they are therefore identical with the corresponding operators in the Schrödinger picture, where we have that the position operator x naught is equivalent to the position operator x of the Schrödinger picture. Similarly, the momentum operator p naught is equal to minus iota times h cross times the derivative with respect to the position. As a result, the Hamiltonian has the form of the Schrödinger equation, which is given as the Hamiltonian operator h unx, where un is a function of x, is equal to minus within brackets minus h cross square by 2m times the double derivative with respect to the position plus 1 upon 2 times mass times the square of the angular frequency times the square of the position whole acting on the function unx, and this is equal to En unx, where En is the corresponding energy eigenvalue of the eigenfunction unx. Here in this equation, the middle term within the brackets, we see that the first term defines the kinetic energy term, while the second term defines the potential energy term, or in other words, the first term defines the term due to the momentum operator, and the second term defines the term due to the position operator, which has the solution that is well known, with the function unx is equal to square root alpha upon under root within brackets under root pi 2 to the power n factorial, this whole times exponential within brackets minus half alpha square x square bracket closed times h subscript n within brackets alpha x. These are the eigenfunctions with the eigenvalues given by En is equal to n within brackets n plus half bracket closed h cross times the angular frequency. Here En is the energy eigenvalues corresponding to the eigenfunctions unx, where alpha is a constant and is defined as m times k upon h cross square whole to the power 1 by 4, and this can be simplified to give alpha is equal to under the root m times angular frequency upon h cross, and h subscript n within brackets alpha x are the Hermite polynomials of diagonal elements of operator p0 and operator x0. Alternatively, one can use the state vectors given here in the Heisenberg picture to determine the energy eigenvalues of the diagonal Hamiltonian operator H. In fact, one can also calculate the off-diagonal elements of both the momentum operator P0 and the position operator x0 using the state un as a function of x. Thus, for the off-diagonal elements of the position operator x0, we can obtain x0 n prime n is equal to under the root h cross by twice m times omega whole times within the bracket under root n times delta subscript n prime plus 1 plus under root n plus 1 whole times delta subscript n prime minus 1 bracket closed. Similarly, we can also define the off-diagonal elements of the momentum operator P0 as P0 subscript n prime n is equal to iota times under the root m times omega times h cross by 2 whole times within brackets under root n times delta subscript n prime plus 1 minus under root n plus 1 times delta subscript n prime minus 1 bracket closed. Here delta is actually the delta function defined for the off-diagonal elements n and n prime plus 1 for the first term within the brackets and n prime minus 1 for the second term within the brackets. Using these relations for the off-diagonal elements of the position and the momentum operator, we get the complete set of the position operator as x as a function of time n prime n is equal to under the root h cross by twice m times omega whole times within brackets under root n times exponential within brackets minus iota times omega t bracket closed times delta function n prime plus 1 plus under root n plus 1 times exponential within brackets iota omega t bracket closed delta function n n prime minus 1 bracket closed. And similarly for the whole set of the values of the of the momentum operator, we get momentum operator as a function of t, that is time, all the values n prime n is equal to iota times under the root m times h cross times omega by 2 whole times within brackets under root n plus 1 times exponential within brackets iota omega t bracket closed delta function n prime minus 1 minus under root n times exponential within brackets minus iota omega t bracket closed delta function n prime plus 1 bracket closed. Comparing with Hamilton's equation of motion, we emphasize over here that these equations are formally identical to Hamilton's canonical equations as defined in classical mechanics. It is thus quite apparent that the Heisenberg picture corresponds to a formulation of quantum dynamics which is formally close to the corresponding formulation in classical mechanics. Finally, the equation of motion for the expectation value of the operator A subscript h, that means the expectation value of the operator A as defined in the Heisenberg picture, can be written as the derivative with respect to time of the expectation value of the operator A subscript h in the Heisenberg picture is equivalent to finding out the derivative with respect to time of the bra vector psi subscript h operator A subscript h as a function of time ket vector subscript h, where the bra vector subscript h and the ket vector subscript h are the state vectors in the Heisenberg picture, and the operator A subscript h as a function of time is the operator A in the Heisenberg picture, which is time dependent. And this can further be written as bra vector psi subscript h derivative with respect to time of the operator A subscript h ket vector psi subscript h, and this is equal to the expectation or the average value of 1 upon iota times h cross whole times the commutation relation of the operator A subscript h and the Hamiltonian operator h subscript h. That means the expectation value of 1 upon iota times h cross the commutation relation of the operator A and the Hamiltonian operator A as defined in the Heisenberg picture. Now, if the operator A subscript h as defined in the Heisenberg picture has explicit dependence on time, then we can rewrite the above equation for the operator A subscript h as the time derivative of the expectation value of operator A subscript h is equal to the expectation value of the partial derivative of operator A subscript h with respect to time plus the expectation value of 1 upon iota times h cross whole times the commutation relation of operator A subscript h and the Hamiltonian operator h subscript h. So students, now let us summarize what we have learned in this module. So, the first thing that we learned in this module was what is the Heisenberg picture. After gaining an understanding of the Heisenberg picture, we then derived the expressions for the Heisenberg's equations of motion. After that, we learned how the problem of the linear harmonic oscillator is studied through the Heisenberg's equations of motion. Then we learned the similarity between the equations of motion in the quantum dynamics and those in classical mechanics. Thank you.